Hello, everybody. Welcome to another video for linguists about Python or about Python for linguists, both of these things. This one is about regular expressions, the first in a series of videos about regular expressions. And quite simply speaking, regular expressions are something you can't get around when dealing with computation for natural language processing. They're not particular to Python. They're a general formalism to search for and match abstract patterns in string data. And regular expressions are implemented in basically all programming languages. So knowing about these has utility much beyond Python. That said, we're talking about them in Python here. As always, these slides come with code examples and exercises, so be ready to engage those. And you get links to the HTML slides where you can look at the results or the potential solutions for the exercises, and those links will be provided. All right, let's jump right in. So when dealing with language data, some of the things we commonly may want to search are things like all singular and plural forms of a given noun, all words ending in "-i's", whether that's spelled with a Z or an S, all inflectional forms of the verb have, like have, has, had, etc. All progressive forms, so all inflectional forms of be followed by a word ending in ing. And some of these patterns may get a bit tricky to approach just with string searches. Not impossible, surely, but sometimes a bit tricky. And this is where regular expressions come in. They sort of allow one search pattern that includes a bit of flexibility. I will say right here, at the beginning of talking about regular expressions, they seemed very powerful to me when I started, and for the first couple of years, I actively used Python. For example, my dissertation work really very heavily relied on regular expressions, and increasingly I'm going back to working with strings and conditionals applied to typically sort of wordless type of data, because that tends to be a bit faster, or not just a bit, but quite a bit faster in implementation, and to my mind also very often more legible when the patterns get complex. But you'll see what I mean once we get into regular expressions themselves, and once we reach a certain level of complexity in these expressions. And that's certainly to some extent a matter of preference, although the just the computational speed is probably um, something a bit more objectively in favor of working with strings in some contexts. But yeah, we'll see this, and even though I'm not using them as much anymore, there's really no way around them. So it makes sense to learn about them, no matter how central they're going to become to your coding. So let's take the first example here. All singular or plural forms of a noun. This is not impossible at all to do with just string methods, right? We can have, assuming we have a word list of tokenized corpus data, we can do a list comprehension and say word for word in word list, and only if the word is house or it's houses, right? That's doable, but that's the simplest pattern. Think about the be followed by an ing form pattern. That gets a lot more complex. Um, for simplicity's sake, we'll stay with the simple example, but still talk about how to do this with regular expressions. What we need to do first is import a module called RE, regular expressions, that allows us to do something. We're not actually going to use anything from this model up until the last line of the little code snippet here. And then we define what's actually a regular expression. But the regular expression itself is just defined, or is just a string, really, right? It's the string house s question mark, prepended with this R flag, that just indicates this is a raw string. Treat every character just as itself and not as something special, some escape character. Then we feed this some test text. This one reads, there are many houses in the city, but not every house is a home. Dot split, so we've got a word list. And then We run a list comprehension here that sort of does the same thing as what's happening here. X for X in my text. That's just word for word in word list here. If, and here we see something new, and this is actually where the regex module, the RE module comes in, re.match. So if we get the value true for this expression, re match, then house re, our regular expression here, applied to x. And x is just a word in our word list, right? So that's the central bit of functionality we're talking about here. Re match pattern string. What does this do? When does it return what type of value or object? Let's piece it apart a little bit more. House re is our houses question mark. The R just indicates it's a raw string. I mentioned that, and I think we've seen this before when discussing file paths on some operating systems. And for the most part, this is really just a string, right? And it is just a string. It's a string houses question mark. But when we read it as a regex, it doesn't just behave like the exact string houses question mark, right? So there's something particular going on with the question mark here. And when you think about what this matches, so in what cases this evaluates to true. Actually, we should probably see this in a live context here for just a second. Go into live coding. I've actually already implemented it here. So this is just the code we just saw, right? Import re, house re is defined this way. Then we have the string or the split string. So the word list, there are many houses in the city, but not every house is a home. And then x for x in my text if re match house re x gives us the list houses and house. So it does what we wanted it to do. How did it do that? That's the question now, right? And the first thing to think about, if it's houses question mark, how does it match house? Maybe applying just raw logic to what's going on here, you could probably get a sense of what the question mark does here. But we'll see a definition or an explanation in just a second. And then we feed all of this to the match method. This is actually sort of what we need the RE module for. This takes a regular expression pattern as its first argument and any kind of string as its second argument. RE match the expression AB to the string A. You can see what the return value of that is. RE match A to the string AB and RE match ice to the string rice. Actually, let's code this so we can all see what's going on with this. Hope I can remember what it was that I actually, as I'm not seeing my example right now. So RE match, and then it's AB to A. Nothing happens, right? That's interesting. That's peculiar. RE match A to AB. Something happens, and it doesn't sort of exactly tell us what happens, but it returns a match object. And it tells us what the match is too. The match is A. And then this was ice and rice, I believe. So the pattern ICE in the object or the string rice. We don't get anything. So this is kind of interesting. The first one maybe isn't so surprising, right? We search for the pattern AB. Well, that's not exactly in A. It's not a substring of A. But ice is a substring of rice. It still doesn't return any match. That's because the match method starts looking right at the beginning of the string that it's fed, and if it doesn't find something that aligns with its first character or first pattern it expects, then it basically aborts. So this actually does not find a match here. That's something important to keep in mind. Whereas something like ice in rice on just string, right, that gives us true. Ice is a substring of rice, but it doesn't start with ice. So that's a notable difference, right? That's basically what I just explained. RE match tries to match a pattern to a given string, starts at the beginning of the string, and then keeps going until the whole pattern is matched, or the pattern can't be matched. And the first time sort of there's a break with the pattern, including if the first character in the string kind of doesn't fit, then it aborts and doesn't return anything. This should be in the second case, it returns a match object. So for matching the pattern A to AB. In the first and the third, it doesn't. And that behavior, that it returns something or nothing, can be used in conditional statements, because returning nothing is evaluated to false, and returning something is evaluated to true. So sometimes that's just enough to filter out all the things you want in, for example, a list comprehension. And then you can also access what's matched, and we kind of saw this already, right? When we looked at the match object. Let me just quickly go back to that. Can't hurt. We looked at this right here, the match object, right? And it tells us the match is in fact A here. So it also remembers what's matched. And so there's a difference here. Match 1, RE match A to ABC, and match 2, RE match ABC to ABC. Both of these will kind of return a match object and evaluate to true if we just use them for filtering, but they're going to return different matches. So match 1 dot group returns A, and match 2 dot group returns ABC. Let's see this in context as well. So match 1 dot group A, ABC. And that's going to be, it's not, if we just want to use matching for conditionals, this really doesn't matter. But we can also, as we'll see later, use regexes to find all instances that match a certain pattern in a corpus. And then it kind of really matters if we extract only a sub-pattern of what we find interesting, or the whole thing, because we want to probably analyze the whole thing down the line. All right. Yeah, really, that's all I wanted to say here. And this right now here is the first slide where we really talk about the intricacies of regular expressions, because at the end of the day, what it comes down to is learning these special characters that open up the possibility of writing not just kind of a string, but a string with flexibility, with wildcard characters, with a certain number of underdefined characters between one thing and another interesting thing. That's kind of really where regexes shine, but where they also get complex. So here's just kind of the first of two lists I'm going to show you of this kind. And these are probably the most common characters here. So the period, full stop character, just matches any character, a letter, digit, space, anything at all. Any one character is matched by a period. So it's kind of the wildcard symbol. The next three things don't in and of themselves match a character, but they modify what is to be done with the character they follow. So an asterisk following a given character basically looks for 0 or more instances of that character. Question mark for 0 or 1 instance. We saw that with houses, right? So houses question mark matches house, because it's 0 instances of S after house, and also houses, 1 instance of S after house. So it kind of makes that character optional. And plus after a character means this character at least once, 1 or more instances. Think about LO plus VE, that matches love, but also maybe in creative online writing, love with 5 O's or whatever, all of that would be matched. And then there's a couple of ways of defining sets of characters. So \W is any alphanumeric character, anything that's alphabetic or a digit. And then a pattern we'll see repeating is \, the same character but uppercase is just the inverse of that. So whereas backslash lowercase w is any alphanumeric character, backslash uppercase w is any non-alphanumeric character. Backslash d matches any digit character. Backslash uppercase d for any non-digit character. Backslash s, any white space. So this could be a space, a tab, I believe a line break as well, but I'm not sure. Line breaks are sometimes the behavior of line breaks is sometimes weird. Definitely space and tabs. And backslash uppercase s is any non-space character, and that can be quite helpful because sometimes we want, you know, words that contain like an apostrophe or a dash, and those aren't matched. Apostrophes and dashes aren't matched with backslash lowercase w. So sometimes the uppercase S is really quite useful for linguistic analysis. All right, and then sort of you you have this list, and then you start piecing things together. You need to get creative, and you just need to get your hands dirty and practice with these. We're going to do that in just a second. But before that, one final thing to introduce is the notion of escaping, right? And there's a logical question you might be having, and that's if the period, the full stop, represents any character at all. What if we just exactly want to match a period? What if we want to match a plus sign, an asterisk, a question mark, right? We can't easily do that, straightforwardly do that, because by default these become these special characters and not just themselves. And in order to do that, we need to escape these by prepending them with a backslash. So backslash full stop actually matches a full stop character. Backslash question mark actually matches a question mark. Backslash asterisk matches an asterisk. And the same thing applies to the backslash itself. So backslash itself is a special character. Backslash means matching a backslash. A little bit tricky to sort of work your mind into, but it's just one of those things you get used to, right? So if you want one or more backslashes, you do backslash for the backslash and then plus for one or more. And if you want a backslash followed by a plus, you do backslash plus. Kind of weird and tricky, but it's really a matter of practice. Speaking of, let's do just that. Write regular expression patterns that will match. First, a sequence of 0 or more letters followed by at least one digit. Be sure to match the entire sequence of digits if there is more than one, so not just the first one, but the entire one. And bonus, you can include an optional decimal point, which is slightly more tricky. The indefinite article a or un enclosed in white space, so with a preceding and following white space. And then you can use re-match the patterns you defined and then some strings you write yourself to see if the behavior is as you would expect it to behave. Pause the video, play around with that, look at the HTML slides for my solutions once you feel like you've exhausted your own efforts on this. And I'll just continue right here with more special characters. This is really, at the end of the day, a lot of it comes down to these special characters. These are not quite as, well, some of them are quite as frequent. Anyway, let's take them one by one. A caret character, which is this little upward pointing little roof type of thing, matches at the start of the string, only right at the start of the string. This is not terribly useful for RE match because we already require this to be at the start of the string, but we'll encounter different methods for regular expressions where this is going to be more important than. The dollar sign matches at the end of the string. This, even with RE match, can be relevant because, for example, it makes sure that we match a pattern and then make sure if we want to find a word, for example, we want to find the word house and not, bad example, not Hauser or whatever. That's a surname, not the greatest example. Let's say we want to find all instances of can, the modal can, right? We don't want to find canon. So in order to make sure we just match can, we can do CAN $sign to make sure that this is then the end of um, uh, the string that we're matching. Backslash B matches a word boundary. And that really only becomes relevant when we're looking at string that includes more than one word. So far we've been talking about applying this to every single word in a word list. Again, in more complex cases that we're working up towards, this is going to become more relevant. And then there's another um, character that modifies how or another sequence of characters that modifies how the previous character is to be read. So curly brackets I is exactly I number of matches for the preceding character, and curly brackets I comma j is between I and j matches. So again, let's think about love, LO curly brackets 3 VE only matches LOO OVE, and LO curly brackets 3 comma 5 VE matches 3, 4, or 5 O's in our love character or love string. Then these square brackets are really important. They basically give alternatives. It's interpreted as one character, and that character can be either A or B or C, right? That's what this is. And something that you very commonly see is this extension of it, A to Z lowercase, A to Z uppercase, all in square brackets. That matches any uppercase or lowercase letter. And that's really important because backslash W doesn't match just letters, right? It matches digits as well. And there is no backslash something method, as far as I'm aware, that matches all just letters. So this is the way to match just letters if ever you need to do that. And then something that gets a bit tricky, we saw the caret already, right? Outside of square brackets, it just means the beginning of the string. Within square brackets, when it's the first thing in the square brackets, it inverts the selection. So whereas without the square brackets, this is either A, B, or C, one character that's either A, B, or C. This here is one character that cannot be A, B, or C, anything but, basically, the logical inverse. And then, as the patterns get more complex, a hugely productive thing to do, a pipe between one regular expression and another matches the first or the second. Again, as we get more complex with these REs, you'll see how this is useful. For example, we might think of matching all inflectional forms of B, right? You could do something like is pipe, am, pipe, are, pipe, was, pipe, were, for example. And then any of these would be matched. Granted, this example doesn't give you much of an advantage over a list, right? Word in list is are, am, etc. But as it gets more complex, it'll become, you'll gain more traction with this. A couple of examples of this. So the regular expression THE $, pipe, AN question mark $. So basically pipe just means everything to its left or everything to its right. So it matches either the and end of the string or a and end of the string or an and end of the string, which is nice because those are the three options we have for articles in English. So that matches all articles. What's the problem if we left out the $sign? I'll leave that for you to ponder or to try out if you don't want to approach it in the abstract. Next example, the pattern square brackets ABC plus, ABC closing square brackets plus, matches any combination of the characters A, B, and C, one or more of them, and it'll stop matching as soon as another character is encountered, right? So it matches A, B, C, A, B, A, C, C, and as soon as there's a D in there or some crazy Y or whatever other characters, weird characters you might think of, then the matching stops. And if the first character in our string, if we feed this to RE match, isn't either A, B, or C, there's not going to be any match object at all. And then finally, backslash W, lowercase w, Square bracket 7, comma 9, followed by a \b word boundary, matches any word between 7 and 9 characters long. Could be quite handy. I don't know particularly what for, but that's how you do it. And again, it comes down to practicing this stuff. So here's an exercise where you actually can apply this to corpus data. So we have the State of the Union corpus on Ilias. It's all of these State of the Union addresses by American presidents in one big text file. Turn that into a word list. Don't worry about cleaning that word list up particularly. This is just for instructional purposes. And apply list comprehensions with regular expressions and matching, so with RE_match, to this list to get the following. A dig or digit list that's all words containing digits. There may or may not be characters in these words, but as soon as a word has one or more digits, it should end up in this list, and everything else should not be in the list. A long list, that's just all the words in the text that are 12 or more characters long. I know we don't need regexes to do this, but please try it with a regex. An ing list, so that's words ending with ing. But let's make it a bit more interesting. Ones that also have an additional vowel preceding the ing ending, either immediately or not. So the logic here is that this should catch things like being, running, etc., but not these monosyllables, king, thing, etc. They behave differently on a number of counts. And we'll assume that A, O, I, E, and U are vowels. And let's just not worry about things like trying, typing, right, where the vowel is really is the Y. The Y letter is just a bit tricky, and let's exclude that particular complication. Generally, as you do this, it's probably a good idea to have some kind of regular expressions cheat sheet, which you can find easily enough by Googling just that. And yeah, sink your teeth into this, and then once you're done, scroll down for the solution that I would propose for all of this. That concludes this lecture. Remember, it's all just pattern matching. There's patterns here that kind of make me a little dizzy, so I'll continue to the image credits and the link to our slides as a QR code, as a spelled out URL, and you can also find it in the video description.